Hello, I'm here to talk to you guys about Thevenin's theorem and max power transfer. So start off with sharing the notes here for you guys. All right, so this is how I like to do things. I got it on camera and stuff. So we've got Thevenin's theorem, max power transfer. We're going to state what Thevenin's theorem is. This is the procedure for determining Thevenin equivalence. Apply Thevenin's theorem to simplify a circuit, analyze some stuff, some circuits, and then we'll talk about the maximum power transfer theorem to solve for appropriate problems. So start off, Thevenin's theorem. It simplifies the analysis of complex circuits, allowing us to replace all of the elements in the circuit with the combination of just one voltage source, which we call VTH, and one resistor, which we call RTH. Okay, so we take this complex circuit here, and we've got some component that we call our load, and we replace everything that's not, not our load with just a simple voltage source and a resistor. Now, how do we figure that out? Well, the Thevenin voltage is the open circuit voltage. Okay, the open circuit voltage at the terminals. What's that mean? That means what is the voltage where our load was when there's no load? So it's an open circuit. RTH is the input or equivalent resistance at the terminals. So the terminals being these 2 points, A and B. That's the output, the load connection points. So at the terminals when the independent sources are turned off or zeroized. Okay. So what's the process for this? Well, the process is, first thing you do for Thevenin is you remove the load from the circuit. Okay. Now this is not on the equation sheet, so you need to remember these steps in order to get at least one of the problems on the test, because it's almost guaranteed that we'll have a Thevenin problem. All right, so remove the load from the circuit. Load is some unknown or variable component that is supplied power from the circuit. Okay. So what we do, we take it out, and then for determining VTH, we measure the voltage where the load used to be. Okay, so we've got this circuit here, and we're trying to figure out what is the voltage between points A and B. Well, first thing that I usually tell people to do is to identify the nodes. So this is how I identify the nodes. Do a little drawing thing. I kind of make it boxy because, well, that just works for me. All right, so these are our nodes. So we can designate, we'll designate that one as ground because it's right next to the source. So we know that this one's at 20 volts because we've got the source there, and that's 20 volts. Now what we're trying to do is we're trying to find the voltage between A and B. Okay, so that's A and B. And between A and B is this 40 ohm resistor. Now, if this is an open circuit, there's no current flowing that way, right? So if there's no current flowing that way, that means that all the current flowing here goes through there, which means that these two components are in series. There's no current going that way, all that's in series. So this is all one big series circuit. If that's a series circuit, and we say VTH is equal to VAB, all right, so it's VAB in this case, okay, VAB is equal to Vs times Rx over Rs. So that's the series voltage divided by the series resistance. And all of these are series. So this is basically an application of the voltage divider rule. Okay. Now Vs is 20 volts. And we've got 40 ohms divided by 80 ohms plus 40 ohms plus 60 ohms. Okay. Doing all that together, we get 4.44 volts. All right. So that's how we can figure out what VTH is. Determining RTH. You turn off all independent sources. Okay. And RTH is the equivalent resistance looking into the dead circuit from the terminals A, B. to make the circuit dead, we have to zeroize all the sources, all the independent sources, okay? What's that mean? Zeroizing a source means setting its value to 0. So for a voltage source, what's a component that has 0 volts across it? So 0 volts across it, that is a short circuit, okay? So 0 volts gives us a short, okay? A current source, 0 amps. So the voltage source, we change it to 0 volts. Current source, we change to 0 amps. And something that has 0 amps through it is an open circuit. So this is an open. So we replace all of our voltage sources with short circuits and all of our current sources with open circuits. Okay. In our example, which we have right here, right, we have this voltage source. We took out the load and we replace the voltage source with a short circuit. And then we look into the circuit from that direction. So it's kind of like we pretend we've got a voltage source there and we're saying, all right, what is the resistance that this voltage source is confronting? Okay. And then we draw our nodes again. Okay. And this time that's all one big node. Okay. And with that, we see, all right, so our source here has these two are connected at that node. So this is in series with that, okay? So the 80 and the 60, so we say 80 ohms plus 60 ohms, okay? All right, and that is in parallel with our 40 ohms, okay? So RTH is RAB, which is the resistance faced by a source placed between A and B, okay? We run through this calculation and we find it's 31 ohms, right? So running through that calculation, you get 31 ohms. So on the next page, I've got it written out so that now we redraw the circuit and we show the Thevenin equivalent with the load installed is, all right, so this was our original circuit. We replace it with a single voltage source and a single resistor. And this voltage source is VTH and the resistor is RTH, okay? And we have to make sure that we label A and B because that's important for the orientation of VTH. So A is the positive side of VTH and B is the negative side, right? So you need to make sure that you label the sides on your load, even though it's a resistor, so it really kind of doesn't matter. But in order to be accurate on what's going on with it, you need the plus and minus with the A and B. So repetitive solutions for various load resistances is easier with this transform circuit because now you can find I load. It's just VTH divided by, because these are now in series, you add them together, total current, so I load is just VTH over RTH plus R load. And the V load, so that's the voltage across that load. V load is equal to, it's a voltage divider. R load divided by the sum times VTH, because it's all in series. All right, so I'm going to skip over the examples for right now and move on to a discussion of maximum power transfer, okay? So, in some applications, the purpose of a circuit is to provide maximum power to the load. So, what are examples of those? And we may ask you some of these. So, really, it's things like stereo amplifiers, radio transmitters. It's things where you want to broadcast. Now, we asked this on a test once, and an original answer that I got that I thought was kind of interesting that works is a searchlight. So you want to get maximum power to that searchlight. So you want to get as much power broadcasting out. That's what these things do. So stereo amplifiers they send power to the speakers and then it broadcasts out, radio transmitters, it broadcasts out through the antenna, communications equipment, same thing, all right? So if you have a system, what load should you connect to that system so that the load receives the maximum power, okay? Well, Thevenin equivalent circuit, which is why we talked about it before we talk about maximum power. Thevenin equivalent circuit makes the analysis simpler, okay? Because you can throw in all different kinds of loads with the circuit and figure out how much power it's going through. So we have the case where the Thevenin voltage and the Thevenin resistance are fixed, the load resistance is varying. So how do we determine our load such that P load is maximized? Okay, well, P load is equal to I load squared times R load. That's the equation that we want to use. That's the good one for a resistor. All right. And we said a little bit earlier that I load was equal to VTH divided by R load plus RTH. Okay, so we square that, multiply it by R load. Okay, we keep carrying it out. We've got VTH squared times R load divided by RTH plus R load squared. Okay, so now we've got, we've got P load in terms of R load and two constants, right? Right side of the equation for P load has only one unknown, R load. So to find the value of R load that maximizes P load, we do some calculus, all right? But I'm not going to go through it with you. So basically, you take the derivative of the equation above, set it equal to 0, and solve for R load. When you do that, you'll find that the R load that we need is equal to RTH, okay? Now, where do we need to remember that? Actually, we don't need to remember that. The fun thing is, on our equation sheet, it's right here. Max power transfer occurs when R load is equal to RTH, okay? That's when maximum power transfer occurs. So the maximum power transferred to the load. Thus, maximum power is transferred to the load when the load resistance is seen. So, and this is known as the maximum power transfer theorem. Okay? When this is true, the source and load are said to be matched. Okay? So you get maximum power when R load is equal to RTH. So it goes up and it peaks right there. We'll probably demonstrate this in a lab kind of thing. All right? So what's that mean for us? All right? So let's continue on. I'm going to keep going through with some discussion here. I'll come to an example here in a little bit. All right, so maximum power is delivered to when R load is equal to RTH. What is the value of this power? Power delivered is, so we've got P load equals, we said it was VTH squared times R load divided by RTH plus R load squared, right? Okay. Now we're going to substitute in R load is equal to RTH. So we've got VTH squared times RTH divided by RTH plus RTH squared. Okay. So RTH plus RTH, that's 2RTH. So we've got VTH squared times RTH divided by 2RTH squared. Well, 2 squared is 4, and we got RTH squared, all right? So we end up with P max is equal to VTH squared divided by 4 RTH, okay? Again, do we need to remember that? No, it's right here, all right? So on our equation sheet, this is still the DC side. R load equals RTH, that's when we get max power. That maximum power is VTH squared divided by 4TH. But this is only true when R load is equal to RTH. It's not true at any other time, okay? only when our load is equal to RTH. Not true when it's not, okay? Now, maximum power delivered to our load, what is the efficiency? Well, efficiency is equal to P out over P in. Well, where's our P out? Our power out is at the load, okay? So power out is equal to I load squared times R load, okay? What's the power in? Well, the power in is the sum of all the power that's dissipated. So we've got I load squared times RTH plus I load squared times R load, okay? And we said when we got max power transfer, our load is equal to RTH. Well, strangely enough, we've got I load squared in all of those. So we've got, this drops down to RTH divided by RTH plus RTH, okay? Well, that's just RTH divided by 2 RTH, or 1/2, which means the efficiency is 50%, okay? So communication circuits, amplifiers, attaining max power transferred is more desirable than attaining high efficiency, okay? High efficiency, that's when we want to get, as much power not lost in our system, but we want power to go to our load only. That means that we want a low RTH, okay? That's the kind of thing when we have, a power distribution system, right? Like, the transmission lines and stuff like that. We want very little losses here. We want all of our losses there, okay? So we don't need to be matching for that kind of thing. For power transmission, attaining high efficiency is more desirable. For those, in those circuits, the load resistance is much larger than the internal resistance of the voltage source. It gives less power, but it's much more efficient, okay? So let's do an example real quick. So we're gonna do this example. So we've got the circuit here on the right. First thing we do, it says, all right, find the Thevenin equivalent circuit. All right, so the first step, we're gonna do VTH, okay? And when we do VTH, we have to redraw our circuit. So we've got plus minus 40 volts. And we draw a 4 ohm resistor and a 12 ohm resistor and a 1 ohm resistor. And we've got an open circuit here. So that's A and that's B, right? Okay. So from A to B, let's see, what do we got? Well, is there any current going this direction? Well, no, because this is an open circuit. So that current is equal to 0. So if there's no current going through this resistor, what's the voltage drop across it? Well, that's 0 volts. So the voltage here is going to be the same as the voltage at this point. Okay, so we can kind of say, well, this is VA plus 0 volts. That makes sense. Okay, so we're going to do our boxes and we'll find out that if we call this one ground, so this is VA, that's going to be VA plus 0 because there's 0 volts across there, and this is VB, and this is 40 volts. Okay, there's no current going that way, so how are these two connected? Well, they're in series. So VAB, which is equal to VTH, is equal to 40 volts times 12 ohms divided by 4 ohms plus 12 ohms, okay? That gives us 30 volts. All right, so that's VTH. Step 2, RTH, okay? So now we redraw the circuit again. This time we've got 4 ohms, 12 ohms, and 1 ohm, okay? A and B. Now, what do we do with our source? Our source was a voltage source. So what do? A voltage source we short, okay? And now that we've done that, we say, all right, we need, that's a node, that's a node, and that's a node. All right, so from A to B, if we pretend like we've got, so we're looking into it from from where the load was, okay? This 1 ohm, so RTH, that 1 ohm is in series with it. So we've got 1 ohm plus, and this 12 ohm and the 4 ohm, they share these two nodes. They're between those two nodes, okay? So because of that, they're in parallel. So we've got 4 ohms in parallel with 12 ohms, right? We add that together, and we get 1 ohm plus 3 ohms, or 4 ohms, okay? So the answer for part A, which is the Thevenin equivalent circuit, is our VTH, which is 30 volts. We've got our RTH, which is 4 ohms. Then we've got A and B, and we've got our load. So that is what our Thevenin equivalent circuit looks like. All right, now B, calculate the maximum power transferred to the load. Okay, so P max is equal to VTH squared divided by 4 RTH. Okay, VTH was that 30 volts. So we take 30 volts, we square it. We've got 4 times 4 ohms. 30 volts squared divided by 16 gives us 56.25 watts. Okay. Number C, letter C says, determine the power dissipated by our load for load resistances of 2 ohms and 6 ohms. All right. So now we're saying, all right, P of 2 ohms, right? So that is going to be VTH. So we need, let's try this again. We've got I squared, I load squared times R load. Okay, in this case, R load is 2 ohms, and I load is VTH squared, divided by RTH plus R load. So that's I load. We square that, and we multiply by R load. Okay, so the P of the 2 ohms is equal to 30 volts divided by 4 ohms plus 2 ohms. That squared times 2 ohms. So 30 divided by 6, that gives us 5. 5 squared times 2. So 5 squared, 25. 25 times 2 gives us 50 watts. Okay, P of the 6 ohms. That one is 30 volts divided by 4 ohms plus 6 ohms squared times 6 ohms, because our load is now 6 ohms. So 30 divided by 10 is 3. 3 squared, 9 times 6 gives us 54 watts. And now you see that 56 is the high. You go down 2, you get to 50. You go up 2, you get to 54. Right? And that's all there is to do. Congratulations. I hope you guys learned something. Thanks.